Hello everyone, thanks for stopping by and welcome to the current state of Linux rootkits. My name is Philip Haas. I am a senior security consultant here at Optiv and I've been with the team for about 4 years now. I have always had a love of all things Linux and have been fascinated with rootkits in particular, and that's what we're going to be talking about today. So for a quick overview of what we'll discuss, we will talk about what a rootkit is, we will give a brief history of rootkits, and then we're going to dive a bit deeper into some specific rootkit archetypes that kind of highlight the evolution of rootkit design over the years. And in particular, we'll talk a bit about LD preloading, we'll talk about loanable kernel modules, or LKMs, and we'll get into eBPF, which is what some of the newer techniques have been utilizing. So, what is a rootkit? It is a post-exploitation tool designed to enable persistent and privileged access to a system while actively hiding its presence. The keyword here is post-exploitation. Rootkits are not really useful unless you have already compromised the system and escalated privileges to root. And rootkits are typically either user mode or kernel mode rootkits, depending on the permissions in the operating system, though some rootkit designs do make use of both modes of operation. Now, kernel mode rootkits operate with ring 0 privileges, which is the same privilege level as the kernel. They are typically programmed as either device drivers or as loadable kernel modules. And while their development isn't necessarily difficult, it can be tricky and kind of fraught with risk, because any errors or bugs in the code can result in an unstable system. And obviously, crashing your victim host when you're trying to remain stealthy is just not a good look. User mode rootkits, on the other hand, they operate at ring 3, along with the rest of the applications on the system. Due to their nature of being outside of the kernel memory space, their design doesn't require quite as much precision as kernel mode rootkits. That being said, you can still absolutely brick a system if you hook a bunch of syscalls and fail to route them correctly after the fact. But in general, user mode rootkits are considered to be more stable and easier to develop. And while they aren't necessarily relevant to the talk today, if you're curious about rings 1 and 2 shown in this image, you don't have to worry about them. They don't get used in Linux. They were originally designed with the intent of providing a hierarchical system of execution contexts, where device drivers and other privileged code would run in rings 1 and 2. But operating systems that were designed to work on multiple hardware platforms, such as Linux, basically had their security model simplified to really only delineate between kernel and non-kernel memory space, so, even if the underlying hardware itself is capable of providing for that finer granularity. So the first concept of rootkits originated in the form of just simple backdoored commands. Once a machine was compromised in some way and you established a backdoor shell, the simplest way to maintain your persistence and to remain under the radar of sysadmins was to backdoor the common tools and binaries that might be able to highlight your malicious activities. So, for example, attackers would go in and they'd modify binaries such as PS and top, so it wouldn't list the backdoor shell process when you ran it, or sum, so that the binary checksums still looked valid, or LSOF, so you couldn't see the sockets and files currently being opened by your backdoor, and of course netstat, so you wouldn't see the port opened by your backdoor shell. And this worked okay, but it left a lot to be desired from a rootkit perspective. First off, this method leaves a lot of forensic artifacts on disk, and second, you can't really account for everything. Some sysadmin somewhere could be using some strange proprietary tool to list processes and connections that you didn't know to backdoor, which would end up getting you burned. First written about in 1998 by Silvio Cesare, and forgive my pronunciation if I butchered that, was the concept of devmem rootkits. Devmem was a character device that provided root privilege processes in Userspace direct access into physical memory, both read and write permissions. So hackers with some clever heuristics would be able to locate various data structures in memory and just hot patch some code directly into them. And it's exactly as bad as it sounds. With that much unbridled power, you could manipulate almost anything inside the kernel, like syscall tables, process lists, network lists, like whatever. But thankfully, most modern distributions have done away with this feature, and you can no longer just scribble all over kernel memory. So this technique just kind of faded off into historical obscurity. And so the world kind of moved on to LD preload based rootkits. And as a quick bit of background for this topic, as you know, a significant portion of all the binaries on Linux systems are dynamically linked with various shared libraries. And you can actually view which libraries are linked to any given binary with the LDD command. So in this image right here, we can see that the output of LDD for the ls binary, and it shows us all the various libraries that it dynamically links with at runtime. And note that there is an order of precedence with these libraries as well, wherein the ones listed at the top of the LDD command output, they are loaded first. And this is relevant because typically dynamic library symbols are what we call weak, and thus they can be overridden by previously linked symbols. And fortunately for all you hackers out there, in libc all syscalls are conveniently wrapped in a library function for you. So, for normal programs, when you run a dynamically linked binary, and for instance it needs to make a write syscall, it will go and seek out the definition of this write syscall, which is actually a wrapper, as mentioned, in the shared library file called libc.so. And as far as that dynamically linked binary is concerned, the write syscall wrapper is whatever the libc library says it is. Okay. Now, within the Linux file system is a special file called the ld.so.preload file. And this is located in your etc directory. This file is significant because any shared library referenced in this file will then be linked to all binaries in the system that utilize dynamic linking before loading any of their other library dependencies. So why is this important? Well, because you can load your own versions of common syscalls functions before the real ones are actually loaded in. Recall that order of precedence thing we just talked about. So with a bit of clever programming, this method effectively allows you to hook the syscall wrappers in libc, allowing you to run your own code before the real syscall is executed. So as a demonstration, the image here shows the output of LDD for that same ls binary, except this time I have set the ld.so preload file to point to my write hook.so shared library. Note that it takes its spot near the top of the loaded library list. I know technically it isn't first on the list, but for our purposes you can ignore the linux-vdso shared library. That is a shared library object that's also loaded into every program by default for some kernel optimizations, but for our case it doesn't interfere with our hooking of key syscalls. So as a quick demonstration, I threw together a basic hello world program, of course, and named it the default a.out. The first lines here are me clearing the ld.so preload file so that the system behaves normally. A simple echo of a blank string into the file, so that's all that's going on there. And when this ld.so preload file is empty, the function just prints the expected hello world string. This is good. But in the next lines, we're going to echo into the ld.so preload file the path to our simple hooked library, which is aptly named hook.so. And now when we execute a.out, the same program behaves in a different way and prints out a function hooked string instead. So this is obviously an incredibly simple example of what can be done with this technique, but the point should be clear. Instead of modifying individual binaries and commands now, LD preloading allowed attackers to hijack the syscalls to blind sysadmins to the presence of the rootkit. So when you run a command like ps, what Linux is actually doing under the hood is opening the proc directory and it's iterating through the list of processes from PID1 all the way to PIDN with a flurry of syscalls like getDents, open, stat, stuff like that. And it aggregates and formats all that data nicely into the familiar output you get at the bottom of the screen here. And same thing for netstat. It's going to open up the procnet directory and iterate through all the connections. So in essence, an attacker will just need to create hooked versions of the syscalls that are being used here, like get directory entries, read, readdir, stat, and all the related siblings, right? And with some clever hooking of these syscalls, an attacker simply has the hooked function look for its malicious process IDs as it's iterating through the proc directory and omit them from the output. And likewise, when it's iterating through the connections and with netstat, it's just going to step over your backdoor shell as it comes across it. And despite it being a relatively older technique, threat actors are still utilizing this method of LD preloading in modern rootkits. Making headlines last year was the so-called symbiote rootkit, which among some other techniques still had a very heavy focus on LD preloading to infect every dynamically linked binary in the system. As mentioned in the previous slide, the authors of this malware utilized the same clever syscall hooking to remove references to itself in the directory listings, and the process listings, and the network listings, etc. But it's important to note that there are some glaring flaws with LD preloading, primarily being that despite the fact that your Linux system is probably almost entirely dynamically linked, there are more than likely some statically linked programs, and statically linked programs are simply not fooled by these LD preload shenanigans. So for like the savvy sysadmin out there who wants to avoid getting burned by these, funny LD preload games, you could have some tooling that is statically compiled, and it'll save you a lot of heartache here. An easy way to obtain some of these static binaries would be to download a tool like the BusyBox static package from your distro's repos. And I have that as an example up here in this picture, right? So I run the dynamically linked ls, and I just get my LD preload demo directory showing here. But if I use the statically linked ls found in the BusyBox, it actually shows the presence of my rootkit shared library here as a quick and dirty example. So yeah, LD preloading, it's cool and all, but what about loadable kernel modules? While LD preloading and command backdooring, they are certainly viable vectors in specific cases. Some rootkit developers eventually decided to leave Ring 3, leave it alone for a bit at least, and create some malicious kernel modules. After all, Ring 0 is all powerful, right? And as mentioned a little bit before, creating loadable kernel modules is not that difficult of a process, albeit a bit tricky, because there's just a plethora of online resources, blogs, and how-to books that you can just buy on Amazon that will just walk you through the process of developing a Linux kernel module. And it's a pretty good vector, because once a LKM is loaded into the kernel, into Ring 0, it's going to run with the same privileges as the kernel itself. So I'm going to run you through a quick demo of how a normal kernel module works, and a little bit later we'll demonstrate some features of a more well-known LKM rootkit. So this block of code here, it's essentially the simplest form of a kernel module that you can create, and it's basically what you'd write for your first Hello World kernel module. If you ever buy a book and you want to learn about it, it's chapter 1 stuff. The majority of this code here is just boilerplate, like Linux and C stuff, and the only thing this module is actually going to do is print a hello source zeroCon string upon module loading, and a goodbye source zeroCon string upon module unloading. So I loaded the module into the kernel, and then I quickly unloaded it, and when we go and check the kernel message buffer to see the fruits of our labor, there it is, hello source zeroCon and goodbye source zeroCon. Simple enough. Now, real quick before we get into the rest of the demo, I just wanted to quickly level set with you all on how Linux syscalls work when you aren't hooking the libc shared library like we were doing with LD preloading, and instead show them how you work with kernel module rootkits instead. So starting at the top of this diagram, we have an arbitrary process living in Userspace. This process will call the system call handler function when it wants to execute a certain syscall, say the write syscall in this instance. So the system call handler will go to the system call table, which contains a memory mapping for like every syscall on the system. And it's going to look through it until it finds the right syscall's location in memory. Execution will then jump to that memory address for the right syscall, perform all the actual function work, and then finally generate a return value, which will get placed into a register before passing control back to the calling process. Not too bad, right? Here we see almost the exact same diagram, but this time around we have a loadable kernel module that overwrites the address in the system call table with the location of a hooked version for that syscall. So now when the calling process wants to execute a write syscall, the system call table will now point to an evil version of the write syscall in memory, and perhaps this new write function has like some keylogger functionality built into it now. And after it performs its evil tasks, it will then dutifully run the real write syscall, so from the user's perspective, nothing's actually amiss. And it's actually critical to make copies of like the original syscalls, because when you're creating a rootkit like this, if you just arbitrarily hijacked the execution of certain syscalls without replacing the expected functionality, you would either quickly alert the user that something is horribly wrong, or you would just completely brick the system, both of which are not advisable. Okay, so now I'll show you some features of a rootkit called diamorphine. Diamorphine is a LKM rootkit with support for most Linux kernels from like 2.6 up, and it is super straightforward to demo it and check it out. You can do it yourself. You can just clone the repo, cd into the folder, type make, and you're ready to INS mod it and play with it yourself. So with diamorphine, when you do INS mod it, it's going to immediately hide itself from the kernel module list. So trying to list out the kernel modules with ls mod here, and it's going to show you nothing, as demonstrated in the image here right above. Now, you interact with this rootkit by issuing certain signals. The particular signal you're going to use to unhide it is 63. So most of you are probably familiar with the kill command, but some of you might not know that despite its name, kill is actually far more flexible than its name simply suggests, because it can actually send any kind of signal you need to any arbitrary process. So if we need to send signal 63, you can just do kill 63, give it an arbitrary process, because diamorphine doesn't actually care. It's just looking for any issuance of the 63 signal call, and it'll unhide itself. So when you ls mod now and grep for diamorphine, there it is. You can actually see it. Diamorphine can also grant the given user root privileges. All you need to do is send a signal 64 to any arbitrary PID, as we show right here in the first image. So you can just do kill -64 and then an arbitrary PID. You run whoami, and we now have root privileges. Pretty cool. Likewise, if you want to hide any file or directory in the system, diamorphine specifies a magic prefix string in one of the header files, as you can see here in the second image. And if you append this magic string to any file or directory on the system, diamorphine will happily go and hide it for you. And so for the sake of this demo, I chose my magic prefix string to be Optiv_SCZ. So if we want to hide our diamorphine directory, the one that we cloned off GitHub, we simply need to rename the file or the directory and prepend our magic string. And ta-da, it's gone. Okay, so we've seen that kernel module rootkits can perform all the same function hooking and obfuscation as LD preload rootkits that we just spoke about a little earlier. Right, so we're talking about hiding processes, hiding network connections, hiding the module itself within the module list, except better, because this time around, even statically linked programs and binaries can be fooled as well. However, it's not without its drawbacks. For one, kernel programming can be a very particular thing. A single small mistake can result in an unstable module that could completely crash a system. Obviously undesirable if you're trying to be stealthy and maintain your persistence. But even if your module is stable and you programmed everything correctly and it works right, the kernel will still detect an unsigned module being loaded, and it's going to mark your kernel as tainted. Now granted, a cleverly designed rootkit like diamorphine actually will go in after the fact and reset this kernel taint flag, But there are ways to reconcile a mismatch between what the kernel reports as a clean kernel and the presence of unsigned modules within memory. It's kind of getting into the field of like IR and forensics, but it can absolutely be done. But that's only if you're even allowed to load a kernel module in the first place, because kernel module signing is a thing, and some systems may be configured to where you simply cannot load an unsigned module. And in those situations, you're just out of luck for kernel module rootkits. Now, I'm going to focus more on prevention here because detection of kernel module rootkits can become extremely complicated depending on the sophistication of the rootkit developer, and could honestly warrant its own separate talk. But there are a couple of things you can do to harden your system, your Linux system, to these kinds of attacks. First and foremost, as we just kind of spoke about in the last slide, simply requiring and enforcing kernel module signing is going to go a long way. But it's important that it's configured to where it's not just going to generate a kernel taint warning, but actually prevent the loading of unsigned modules. And if your use case allows for it, you can even entirely prevent loadable module support, if that's a feasible option for your system. Alternatively, consider configuring your system to enforce kernel lockdown mode, specifically the confidentiality mode seen here. If you know that you're not going to be needing tracing or probing features for your kernel resources, this is a good option. If you do need tracing or probing features, though, there's a slightly less restrictive integrity mode, and that could be a good option. But it's important to note that these solutions are aimed at providing kernel integrity, not full system integrity, right? A malicious user could still have root access to your system, which would be bad, but if you can at least know that the kernel is trustworthy, you can at least trust the output that you might be getting from your various kernel subsystems, like the audit subsystem. Somewhat new to the scene are the development of eBPF-capable rootkits, which extend the capabilities of traditional rootkits even further. So for a quick primer on eBPF, it stands for the Extended Berkeley Packet Filter, and it's basically designed to safely extend the capabilities of the kernel without, one, requiring changes to the source code, or two, loading any kernel modules. But it has expanded so quickly, like in the last 4 or 5 years, that any comparison to the classic BPF is like hardly relevant anymore. But eBPF itself is a system within the Linux kernel that allows you to create these programmable trace points, known as eBPF programs. So these programs can be attached to any entry and exit points to kernel functions, so like that includes syscalls. They can be attached to normal Userspace functions, both entry and exit, and they can even be attached to network interfaces to observe and modify network traffic. So one cool thing about eBPF programs is that they're designed to be portable across multiple versions and architectures, so long as the kernel supports it. But as with other rootkits, you do need elevated permissions still. So, unless unprivileged eBPF is enabled for whatever reason, all processes that intend to load an eBPF program into the kernel must be running as root or have the cat BPF capability set. Now, eBPF programs are what we call event-driven, and they are executed when the kernel or an application passes a certain hook point. So there are several predefined hooks that we can make use of, and these include syscalls, they include function entry and exit hooks, kernel trace points, and even network events, as we kind of mentioned in the last slide. So let's take a look at syscalls, for example, highlighted in the red box in the top left here. If we attach an eBPF program to the entry point of a syscall, we can observe and modify the parameters that are being sent to the kernel. And likewise, if we attach an eBPF program to the exit point of the syscall, we can observe and modify the response being received from the kernel. As a bit of a practical example, let's review a very simplified breakdown of the system, checking to see whether a user has or a user is allowed to exercise sudo privileges. When a user runs sudo, among many other checks, the program is going to go and look at the etc sudoers file to see if that calling user is present in the file. It does this by issuing an open@at syscall for the etc sudoers file. So the syscall will return a file descriptor for the program to use in the subsequent read syscall, as you can see in this diagram. In this example, we were returned file descriptor number 13 for the etc sudoers file, which is then plugged into the read call and sent back on its way. Now the kernel is going to return the contents of the etc sudoers file into the specified buffer, which it's buff in the read syscall, and it will then hand control back to the application. And the sudo program will go and check to see if our user is indeed present in the etc sudoers file. So as a demonstration of how eBPF can modify files on the fly, we will take a look at our same diagram here, but this time with hooks visualized in these red boxes. So imagine we hooked the openat and read syscalls, and we monitored for any instance of when a compromised user account tried to execute sudo. In this case, an eBPF program could intercept that syscall, save the file descriptor that is being returned via the openat syscall, and then have the contents of the buffer that are later being returned by read modified to just include a line saying, for instance, www.data is allowed to become root. And I know that this example is perhaps a bit trite, but maybe you have a hidden web shell on the server that allows you to come back anytime as the www data user, but you want to be able to quickly reclaim your root privileges. Now, there is a fantastic assortment of malicious BPF demos out on GitHub under the collection Bad BPF by a user called Path to File, which I found extremely helpful during my research. And using this Bad BPF collection, we can actually demonstrate the previously discussed example with the sudo add BPF program. So, as you can see in the top picture, we start as the www-data user, and checking for sudo privileges reveals that we in fact do not have any such permissions. But in the second image, running the sudo add BPF program and specifying our username of www-data, we effectively hook sudo's reading of the etc sudoers file, as we just kind of talked about in the last slide. And we're going to modify it to return for the return value to include this compromised user. The third image shows the result of this. Operating as the www-data user again, we can now run a passwordless sudo command, and it shows that we are in fact root. And finally, the fourth image here shows that from the perspective of anyone else on the file system, the etc sudoers file remains unchanged and untampered with. We can grep for that username and find nothing. And this is because we are not modifying the file itself, but only the temporary buffer that is being returned from the kernel syscall. So that is cool and all, but how does this really differentiate itself from kernel module rootkits? And I'm going to reference this diagram again from before, because now I want to focus on the bottom right here. For a bit of background, there is something called XDP, or Express Data Path, which is a feature that allows any BPF program to run before the network interface card hands over traffic to the kernel networking stack. Now, as you can imagine, this is a very interesting location for malicious activity to occur, because a rootkit could theoretically modify network traffic before normal kernel processing can be performed or logged. So you could configure C2 infrastructure to communicate at this layer, and it would be quite effective in remaining outside of the view of the kernel and any kernel level security functions. So a lot of your standard security tooling on Linux just wouldn't catch this behavior. There's many instances that have been revealed in the past few years that have been actually going back for over a decade now, like BVP47, BPFDoor, Symbiote, and some others. These are all rootkits that have been found to be using these eBPF features. So that's all kind of scary, right? What can we do to protect ourselves against these eBPF-based threats? Well, there's a few things. First off, you're going to want to monitor all the loaded eBPF programs on a system, as well as their associated data maps, using a tool like BPF Tool. It's on GitHub, it's free, it's open source, check it out. Second, you're going to want to assign the lowest possible privileges to eBPF programs for their expected functionality. And you need to ensure that the procsys kernel unprivileged BPF disabled flag is not set to 0. It needs to be set to either 1 or 2. And finally, you're going to want to monitor your network using IDSs and other network-based firewalls, because you're going to need to detect any suspicious or anomalous communications on the wire, to kind of get ahead of this, right? Because host-based firewalls, they might detect outgoing traffic, but incoming malicious traffic could be tampered with by XDP before the firewall even knows anything has happened. And actually, something else of interest is the introduction of eBPF signing. Now, this is unfortunately still something of a work in progress, but in theory, this would work exactly the same as kernel module signing is, where the kernel would only permit the loading of an eBPF program if it had been signed by a trusted entity. So that's it. I appreciate you guys coming out to listen to me ramble about rootkits for a bit. Any questions and comments you may have, hit me up in the Source Zero Discord, and I'm going to do my best to respond. Thanks, everyone, and have a great day.